Welcome to this deep dive. Um, if you're listening to this, you're probably the kind of person who likes to stay ahead of the curve.
Oh, absolutely.
You want to understand where technology's actually heading, but, like, you also want to avoid drowning in a sea of meaningless jargon and, hype.
Yeah, there's a lot of that out there right now.
There really is.
Yeah.
And because you pay attention, you've almost certainly noticed a completely maddening quirk about modern artificial intelligence.
Oh, I know exactly where you're going with this.
Right. It can be utterly brilliant in one chat window. Like, it will solve a complex logic puzzle or write elegant code or deeply analyze a spreadsheet.
Yes,
But the second you open a new window, it completely forgets who you are.
It is a profound disconnect in our daily workflows. I mean, we are interacting with systems that successfully mimic high-level reasoning, empathy, logic.
Yeah.
But they completely lack the fundamental continuity that we naturally expect from, any intelligent entity.
Imagine hiring an absolute genius
Yeah.
as an executive assistant.
Yeah.
And their daily work is flawless.
Right.
Their analysis is perfect. But every single morning, they walk into the office with absolutely no memory of yesterday.
That sounds like a nightmare.
It is.
No.
Before they can do any work, you have to spend an hour re-explaining the core business, your personal preferences, and, the history of the project they were literally just working on.
You would fire a human for that on day 2.
Exactly.
Yeah.
Yet that is the default state of AI today, and we just sort of accept it as the cost of doing business.
Well, the tech industry has certainly recognized the friction, and they have spent the last few years frantically trying to patch it.
Right.
But those engineering patches are starting to buckle under their own weight.
Which is exactly why today's mission is so critical. We are unpacking a revolutionary framework designed to cure this AI amnesia once and for all.
I'm very excited about this one.
Yeah, so we are looking at a May 2026 white paper by Kelsi Guidry, which, interestingly, was actually written with research and drafting assistance from Anthropic's Claude.
Oh, wow.
Yeah. The paper is titled A Cognitive Architecture for AI Agent Memory. And the core premise is incredibly bold.
It really is a massive shift in thinking.
Guidry argues that the current tech industry's band-aid for AI memory is just fundamentally broken. Like, if we actually want a system that remembers us, we shouldn't be looking at better databases.
No, not at all.
We need to look at the only system in the known universe that actually does memory perfectly.
The biological human brain.
Specifically, the multi-store model.
Yeah, the foundational argument here is that the tech world basically misunderstands what memory actually is.
How so?
Well, they treat memory as a physical place where you put data, a destination basically, but cognitive psychology tells us memory is not a destination.
Right.
It is a highly dynamic, layered, and, active computational process.
To really appreciate the biological solution, I feel like we first have to diagnose the engineering disease we're dealing with right now.
Yeah, that's a good way to put it.
In the enterprise tech world, the industry standard fix for this AI amnesia is something called RAG, retrieval augmented generation.
Yes, the famous RAG.
But let me push back on how RAG is usually sold to us as this magical memory fix. Isn't RAG basically just taking a giant filing cabinet of Corkit documents and bolting it onto our amnesiac genius?
That is pretty much exactly what it is.
So the genius still has no actual internal memory? We just handed them a faster way to rifle through the files when we ask a question?
The tech industry loves that filing cabinet analogy, but it masks a catastrophic functional flaw.
Oh.
Yeah. What's fascinating here is how the white paper pulls from Pengfei Du's March 2026 survey of LLM agent memory to explain this failure.
Okay, lay it on me.
So in human cognitive psychology, forming and recalling a memory involves at least 4 distinct sequential functions.
Okay, 4 functions.
First is encoding, which is giving new information contextual meaning. Second is consolidation, which is integrating that new meaning into your existing worldview.
Right, connecting the dots.
Exactly. Third is storage, where the data safely lives. And fourth is retrieval, the actual act of pulling it back up when needed.
Okay, that makes sense.
But RAG takes all 4 of those complex, highly distinct cognitive functions and just collapses them into a single flat database query.
Wow. So we are basically treating an intricate cognitive process like a crude CTLF search command.
It's actually worse than that.
Really?
Yeah, a CTLF search at least assumes all the text is equally valid. RRAC has zero concept of what information is actually important to the user versus what is trivial.
Oh, I see.
It has no biological notion of recency or how useless memories should naturally decay over time.
So it just hoards everything equally.
Yes, and most critically, it has no idea what older information has been explicitly superseded by new information.
Because it's just a filing cabinet.
Right. You just shove raw PDFs into the cabinet, and the AI blindly pulls out whatever paragraphs happen to have matching keywords.
Regardless of whether that information is like a decade out of date.
Exactly.
Okay, let's unpack this. If our garage is a dead end because it treats memory as a flat table, what does a dynamic biological model actually look like for a digital brain?
Well, according to the paper, the blueprint starts with a framework from cognitive psychology dating way back to 1968.
Wow, 1968.
Yeah, it's the Atkinson-Shiffrin model. And this model begins exactly at the boundary where the outside world hits the brain. The architecture introduces layer 1, which is sensory ingestion.
Okay, so layer 1 is sensory ingestion.
Now, this serves as the absolute front door of the entire system. Every single thing the AI is exposed to hits this layer first.
So user text messages, voice transcripts, PDF files you upload, URLs that scrape.
All of it.
It all lands here in an unlimited, raw, completely unfiltered format. It feels like the AI is just keeping the physical receipt for every single thought or input it ever encounters.
That's a great analogy. The biological parallel is human sensory memory, which is, vast but incredibly brief.
Like when you visually take in every leaf on a tree as you walk by.
Exactly. But most of that data decays instantly because you don't focus on it. However, in an engineering context, capturing all of this raw data cheaply serves a massive, non-negotiable purpose for enterprise AI.
And what's that?
Provenance.
Ah, provenance. Meaning the system can definitively prove exactly where a piece of information came from.
Think about the disaster scenarios of current AI. If you deploy an AI agent in a corporate legal department or a medical diagnostic setting, accountability is everything.
Yeah, it absolutely is.
It cannot just vaguely guess where it heard that a specific drug dosage was safe.
Right. That would be terrifying.
Because every single memory the AI eventually forms in this new architecture must physically trace back to a raw sensory record in layer 1. The AI can finally answer the question, where did I learn this?
Without hallucinating.
Exactly. It pulls the raw receipt.
That structural accountability is huge. So layer 1 is the giant permanent box of raw receipts.
Right.
But you can't work out of a box of receipts. That brings up layer 2, which is short-term or working memory.
Yes, moving up the chain.
If layer 1 is the receipt box, layer 2 is the active physical workspace on your desk. You can only fit so many open folders on your desk at once before things start sliding off the edges onto the floor.
The desk workspace analogy maps beautifully to the fundamental limitations of large language models.
The context window, right?
Yes. Every LLM has what is called a context window, which is the absolute maximum amount of text measured in tokens that it can actively process at any given millisecond.
And that context window is a hard mathematical ceiling.
It is the exact AI equivalent of human short-term memory limits.
It reminds me of Miller's magic number 7.
Oh, yeah.
The famous psychological concept that human working memory can generally hold about 7 discrete items, plus or minus 2, before we start dropping things.
That's a perfect parallel. And just like the human brain, when you push an LLM past its context window, it doesn't just slow down or give you a polite warning.
It just starts dropping files off the desk.
It begins silently forgetting the earliest things you told it in the conversation. The papers literally fall off the back of the desk into the void.
That is so frustrating when that happens.
People in the tech industry frequently confuse a massive million-token context window with actual memory. But as the Jew survey emphatically points out, long context is not memory.
If your desk is the size of a football field, it is still just a temporary workspace.
Exactly.
The temporary nature is the real kicker here, because the biggest problem with the desk is that when the workday ends, like when you close the chat window, that entire desk is wiped completely clean by the system.
The workspace just vanishes.
So how do we save the important insights before the workspace clears? We need a structural bridge between the temporary desk and the permanent archives.
And here's where it gets really interesting.
The white paper introduces layer 3, the consolidation bridge. And the biological metaphor they use for this mechanism is sleep.
Sleep is the most architecturally profound layer in the entire framework. And frankly, it represents the missing link in almost every AI startup today.
Why is that?
Well, in humans, memory consolidation heavily relies on sleep, particularly the slow wave and REM cycles. During those cycles, your brain isn't just taking the day's raw events and dumping them into a biological folder.
Right, it's doing work.
It is doing heavy computational work. It is actively reorganizing neural pathways, pruning useless data, and abstracting specific events into general rules.
The paper argues AI needs to do the exact same thing, but crucially, it needs to do it asynchronously.
Yes, exactly.
The AI shouldn't be trying to analyze, cross-reference, and file away complex new knowledge while it is actively trying to chat with you.
Because consolidation is incredibly compute-heavy. It involves the system asking itself a series of complex questions. Like, what specific data from this chat is actually worth keeping? How should it be structurally encoded? What older facts does this new information replace?
That's a lot of background processing.
If you force the AI's processing unit to do all of this on the critical path of the user interaction, the chat interface would just freeze.
The cursor would just blink at you for 5 minutes while it thinks.
Exactly. Therefore, this heavy lifting must happen offline, operating in the background, exactly like human sleep.
Let me bring in a highly specific example from the paper that made the mechanics of this sleep phase really click for me.
Go for it.
Let's say on Monday, the AI learns through a chat that a client uses a PostgreSQL database. But then on Friday, in a totally different chat window, you mentioned that the client just migrated their entire backend to MySQL.
Okay, a very common scenario.
In the standard flat rig system we talked about earlier, the AI just blindly stores both facts in the filing cabinet.
And the consequence of that is catastrophic.
Why?
Because the next week, when you ask about the database, the AI retrieves two completely contradictory pieces of information that have equal weight.
Oh, man.
And it either hallucinates an answer or just breaks down in confusion.
But through this active consolidation phase, during its digital sleep, the AI performs a mechanism the paper calls supersession.
Supersession, yes.
It actually analyzes the two facts, recognizes the logical conflict, flags Monday's PostgreSQL memory as historical context, and explicitly marks Friday's MySQL memory as the current overriding truth.
It permanently resolves the contradiction before the user ever experiences a problem.
That is brilliant.
But supersession is just one part of the bridge. The consolidator is simultaneously running relevant scoring.
Okay, what does that do?
It's actively looking at the transcript and filtering out the social lubrication. It inherently knows that your passing comment about the rainy weather in Seattle doesn't need to be saved for eternity.
Thank goodness. Nobody needs an archive of small talk.
Right. And finally, it performs encoding. It takes the highly relevant, updated facts and formats them. It doesn't just save a raw text dump.
Right.
It writes a highly structured, human-readable document, essentially a perfectly clean summary of the new knowledge.
So the AI has slept on the day's information. It has filtered out the noise, updated the conflicting facts, and written a beautifully clean summary document. But where does a digital brain actually store a summary so it survives a system update? We step into layer 4, long-term memory.
This is a crucial layer.
I have to admit, reading this specific section, I found myself questioning the engineering logic a bit. The paper insists on having a 3-headed long-term memory system.
I know, it sounds redundant at first.
It really does. If the ultimate goal of modern tech is to be streamlined and efficient, why construct 3 different parallel storage spaces? Like, why isn't a single state-of-the-art vector database enough to hold the memories?
If we connect this to the bigger picture of how modern data architecture functions, conflating the actual memory itself with the search index you use to find it is a ticking time bomb.
A ticking time bomb. Okay, explain that.
Well, the math behind AI is moving at breakneck speed. Embedding models, which are the complex algorithms used to turn human text into searchable numbers in a vector database, are constantly being upgraded.
Right, there's a new model every week.
Exactly. Think of a vector database like a massive map with billions of coordinates. The embedding model is the key that tells you what those coordinates mean.
Okay, tracking with you.
If the only copy of your AI's memory is locked inside that vector format and your IT department decides to upgrade to a newer, better embedding model, the old map key becomes completely useless.
Wow. The coordinates suddenly point to the middle of the ocean.
Exactly. So your AI essentially suffers a traumatic brain injury and loses years of learned context just because you upgraded the search software.
That is terrifying for an enterprise.
Which is why the white paper heavily advocates for 3 distinct co-located stores. First, and most importantly, you have the canonical store.
The canonical store.
This is the ultimate, unshakable source of truth. It consists purely of human-readable markdown files, just simple, durable text.
So if the search index completely breaks down, the actual memories survive untouched.
Exactly. It's future-proof.
I could literally open the text file on my own laptop and read the AI's memories myself.
You could. The second component is the retrieval index. This is the vector database. Its only job is to be optimized for blazing fast semantic queries.
So it holds the map coordinates.
Yes, but those coordinates just point back to the canonical text files.
It makes perfect sense.
And the third component is the provenance archive. This loops all the way back to layer 1, the raw sensory receipts we discussed earlier, ensuring the AI can always prove its work.
The triad makes perfect logical sense when you frame it around durability. The text file is the actual memory, the vector database is the fast map used to locate it, and the raw archive is the legal proof the event actually happened.
You've got it perfectly.
Now, the paper mentions these memories get sorted into biological categories. Episodic memory for specific events, like a meeting, semantic memory for general facts, and procedural memory for skills.
Yes, that categorization is key.
But creating a durable archive is only half the battle. How do we get the right memory out at the exact right time without reverting back to treating the AI like a dumb search engine?
That structural challenge brings us to layer 5, retrieval as active cognition.
Active cognition.
The core philosophy here is that pulling a memory shouldn't just be a passive lookup. The act of retrieving information must be dynamic, and it must alter the system itself.
I know educational psychology talks heavily about the testing effect, like the proven phenomenon where if I actively test myself on a fact, I remember it significantly better than if I just passively read it in a textbook.
Right.
I assume this cognitive architecture borrows that biological mechanism. Like, the more the AI retrieves a specific file, the stronger that pathway gets.
It maps directly to what the paper terms use-dependent reinforcement.
Use-dependent reinforcement.
Every single time the AI successfully retrieves a specific memory to help answer a user's prompt, that memory gets a mathematical bump in weight.
The neural pathway gets stronger.
The system organically learns, this specific piece of client history is highly relevant to this user's daily workflow, making it even faster and easier to retrieve tomorrow.
It naturally bubbles up the things I actually care about without me having to manually tag them as important.
Exactly. But there is an inevitable flip side to that biological coin. Memories that are never used naturally experience decay.
Decay.
If a piece of information is encoded but never retrieved over several months, its mathematical weight slowly drops. It sinks lower and lower in the retrieval rankings.
Which forces us to talk about something that is, frankly, very uncomfortable in the tech world. Forgetting.
Oh, yeah. People hate talking about data loss.
We have built an entire global culture obsessed with hoarding all our data forever in the cloud.
We really have.
But in this biological architecture, forgetting isn't a glitch. It is an essential feature to keep the AI sane.
This raises an important question about user trust, and it is something the author, Kelsi Guidry, explicitly clarified in version 1.1 of the white paper after some initial pushback.
Okay, what was the clarification?
In this framework, cognitive decay does not mean deletion.
That is a massive distinction for anyone worried about losing their data.
It is the critical nuance. When a memory decays due to disuse, it is simply being deprioritized in the ranking algorithm. It drops to the absolute bottom of the list so it doesn't constantly clutter the AI's active workspace and drain compute power.
But it is still safely resting in the canonical text store.
Exactly. If a highly specific cue triggers it a year from now, it can be instantly pulled back to the surface.
That's reassuring.
Explicit permanent deletion of a memory is strictly reserved for things like legal compliance, GDPR privacy requests, or, manually correcting a hard error in the system.
We as humans can't selectively delete a bad memory just because we want to, but an enterprise AI obviously has to have a manual override for compliance reasons.
Absolutely.
But looking closely at layer 5, there's an open question here that the paper admits isn't fully solved.
Oh, the self-reinforcing error?
Yeah. If retrieving a memory makes it stronger, what happens if the AI accidentally learns something totally incorrect and then keeps retrieving it to answer questions?
You enter the dangerous loop of the self-reinforcing error. Because of use-dependent reinforcement, if the AI pulls up an incorrect hallucination and uses it in a response, that bad memory gets a bump in weight.
Oh no. So it believes it even more.
It effectively reinforces its own delusion, making it more likely to use that bad fact next time.
How do you fix that?
Well, Figuring out how contradictory evidence from the real world can actively weaken a bad memory pathway, rather than just passively waiting for the bad memory to decay from disuse, is still a highly active area of cognitive research.
So what does this all mean for you, the listener, trying to navigate the future of tech if we step back and look at the entire massive architecture?
It's a lot to take in.
It is. The core takeaway here is that if we want AI to actually function as a reliable, personalized agent, something we can deeply trust over months and years of collaboration memory, cannot just be a flat table of PDF documents.
No, it just doesn't work.
It must be a multi-stage cognitive process. It takes 5 distinct layers.
Sensory ingestion to catch the raw receipts.
Right. A short-term workspace for active thought.
An asynchronous consolidation bridge where the AI essentially sleeps to process the day.
A tripartite long-term storage system to protect against system updates.
And finally, active dynamic retrieval that strengthens with use.
That is the biological blueprint required to turn an impressive language model into a true agent that actually learns, updates itself, and can trace every single thought back to its source.
It represents a profound philosophical shift in how we approach software engineering.
It really does.
We are moving away from simply bolting on cheap external storage and moving toward actually mimicking the functional, messy flow of human cognition.
It is vastly more complex to build.
Oh, incredibly complex. But it is the only viable path to achieving genuine continuity with our digital tools.
But as with any groundbreaking theoretical model, there are still fascinating puzzles left to solve. And I want to leave you with one final thought to chew on, extending an open question from the source material.
This is my favorite part of the paper.
The white paper openly admits that storing procedural memories, which are essentially an AI's specific skills, like how to execute a complex software workflow, storing those as text-based markdown documents feels like a very loose, awkward fit.
Yeah, it's clunky.
It makes perfect sense to store historical facts and episodic meeting notes in text files. But procedural memory in human beings is muscle memory.
Yeah.
It is the innate knowledge of how to balance and ride a bike, not the ability to read a textbook explaining the physics of a bicycle.
Having an AI agent pause to read a massive text file of step-by-step instructions every single time it needs to perform a routine, complex task is inherently inefficient and computationally expensive.
So we leave you to ponder this. If facts and historical episodes are easily and durably stored as text files, how will the cognitive architectures of the future actually store an AI's muscle memory natively?
It's a great question.
How do we encode a digital reflex? Because until we solve that piece of the puzzle, our amnesiac genius might finally remember exactly who we are and what we discussed yesterday.
But we still might have to hand them the instruction manual for the coffee machine every single morning.